Okay guys, let's take a look at today's lesson. We're actually going to look at two different topics today. One is on interpreting graphs of functions and inverses, or of functions, and so this really, you probably haven't done a whole lesson on this before, but it's an important topic for us in calculus that we are able to read and interpret graphs. The second part of this is inverses, and I know you dealt with inverse functions last year in Algebra 2, so this should be mostly a review with the inverses, so that's kind of what we're going to work on. So on this particular graph right here, the f of x is the dashed line, so that's f of x, and g of x is the solid one. Okay, so when we read through the questions, we just need to pay attention to which graph we're referring to. So the first question is, they want us to find f of -1. So we basically just go over here, look at an x value of -1, and we want the f, so that would be right here. So that would be 6. So pretty straightforward, right? That's what we're doing. We're just kind of reading information off the graph. So this was 6. Here, they're really wanting, this is a kind of a weird notation right here, which is why I wanted to do one like that, just so that we're aware what that means. It really means what they're asking you to do is to do f of 3 plus g of 3. I mean, that's what they want you to do. Use each function's y value at 3. So as we go over here and look, we're taking a look at the y value at 3. So here's one y value and there's the other, and we're supposed to add those together. So it looks like 6 plus a -6. So that would be the f -6 plus 6, or 0. Okay, so just that, right, pretty straightforward. Okay, so these are just values. And like on number 3, we're just going to multiply 2 times f of -1, and then we're going to subtract g of -6. So we just go over here, find f of -4. So f would be right here. And then we would find g of -6, which would be right here. And then we just use those y values. So it's going to be 2. So we'll have 2 times 6 minus, and then the g value at -6 was a -2. And we do our, arithmetic basically, and we get 12 plus 2, or 14. So those are pretty straightforward. I think we should not have what I have seen is the most common mistake is just using the wrong function. So just pay attention to which function that it's asking you to use. Number 4 is just one more complex. Again, we're going to read these values off of the chart. So g of -8. So let's go over here. So we're looking for, let's see, -8 would be here. So we're looking for this value. G of -8, which is a -2, plus f of 0. So f is the dotted line one. Let's see, where are we? Here's f of 0. And then we want to divide that by g of 0, which would be this one. So that gives us basically -2 plus 3 over 4, which is 1/4. All right, we okay so far? Okay, great. So now let's get to a little bit more abstract use of the graphs. So number 5 asks the values of x such that g of x equals 4. Let's think about what that means. G of x equals 4 means the y value of g is 4, right? The y value of g is 4. So we go over here and we look. So we said that g was the solid line one. So this is g. And we want to look to see where the y value is 4. So what I usually do is just draw a line right here at 4. And I can see there's 2 locations that g has a y value of 4. This one is on, on the little cross right there. So that, is 4, a y value of 4. This one we are going to have to approximate. It's like between 0 and 1. So we're just going to call it 1/2. Actually, it's between -1 and 0. So we're going to call it -1/2. 1/2. 1/2 and 0. So we're going to call it -1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1/2. 1 Okay, so our answer where they're the same is going to be where x is negative 1/2 and 4. Okay, so you'll just be interpreting your graphs that way. Number 6, a little bit more abstract. So let's look at number 6. They give us a polynomial and they say for what values of x is p of x equal to g of negative 3? Okay, let's think about what they're asking. P of x is a y value, right? And g of negative 3 is a y value. So we need to go over to the graph and find g of negative 3, right? And replace that with here. We're going to put that right here, right? And then solve the quadratic. That's all they're asking us to do. We just need to be able to understand, interpret what they're asking us to do. So let's do that. Let's go over and find where g of negative 3 is. Okay, g of negative 3 looks like that is a 2 right here. So we'll go over here and we'll do what that says. So we're going to say 2 equals x squared plus 2x minus 13. We move everything to one side and we get x squared plus 2x minus 15 is 0. We have several techniques we can use to solve quadratics. We're aware of those. We hope for I hope for factoring is what I hope for. This actually is factorable. If it's not factorable, we have other techniques, right? Quadratic formula, completing the square. I mean, we have other things that we can do. But this factors to be x plus 5 and x minus 3. So our two answers here, the values of x, are going to be x is negative 5 and 3. Okay, we doing okay? All right, let's take a look at number 7. We want to find the values of x such that f of x equals g of x. Okay, so we want the y values of each to be the same, right? So that's basically where they intersect. So let's look at that. Okay, so let me do a little bit of erasing so we can see what's going on here. Okay, so we would like to see where they intersect, where their y values are the same. How many places does it look like that they intersect? 2. There's 2 places, right? There's one here, which we actually already looked at that spot. That was negative 1/2. And there's one right here, which we can see is 9. So our answer for number 7 is going to be where x equals negative 1/2 and 9. Okay? Since we're here, let's just look at number 9. We'll go to number 8 in just a moment. Number 9 says the values of x such that g is increasing. Okay, so let's remind ourselves what it means to increase as we are reading the graph from left to right like we read a book. Right, from left to right, so we're moving this way. As we move this way, if the graph is rising, then it's increasing. Right, I'm pretty sure we've talked about that before. So we're looking and we want to know where g is increasing. So that's the solid line. So here, g is constant, right? It's not moving. I mean, it's moving, but it's not rising or falling. It's staying the same. So we would say that it's constant there. So that's not where. So let's see. Looks like we've got some right through here, right? We're rising through here. So from this location to this location, g is increasing. We all okay with that? So that's going to be an interval. That's an interval where g is increasing. G is increasing from this location, which is negative 6, to this location, which is 3. And then we can also see that g is increasing again over here, right? It's going up. So from this spot to this spot. So let's see, that is at 9. So from 9 to, and where's that going? That's like 11. Okay, and typically on increase, decrease, we don't ever do brackets. Just saying, don't worry about brackets on increase, decrease. We just do parentheses regardless. That would be safe, a safe bet. All right, so that's number 9. And let's look at 10. The values of x such that f of x is constant. F is the y value, right? F of x is the y value. We want where the y value of f is constant. So let's look at it. Let's see. F was the dotted line one. And we see right in here, the y values are all the same, aren't they? For f. They're all the same. That means that it's constant. The y value is constant. So this would be from this location. So what is that? That's -6. So -6 to -1. And the last one on this is number 8. Let's go look at it. Now we want to know, where is f larger than g? And again, we're concentrating on y values. Where is the y value of f larger than the y value of g? So let's go check that out. Okay, so the y value of f larger. So the dotted line. So we want to know, where is the dotted line larger? If we look at it, let me get some of this out of the way. Right here. Am I allowed to talk about this spot over here? No. I mean, f doesn't even go over here, right? F starts right here. So I can't talk about, -11 to -9, because it says there's nothing there to compare. We're comparing y values. Where is f bigger? So we say here, right? And then it's to, this little spot right here. Okay, is there anywhere else that f, the dotted line one, is the y value is larger? There is not. So the answer for number 8 is just the interval from -9 to 1/2 to -1/2. Okay? So that's the lesson on the graphing. So you'll see there's just lots of opportunity, a lot of different things that I could ask, right? We just need to be able to read the information off of the graph itself. So let's go to the next part on inverses. So let's look at this text. So let's first talk about one-to-one functions. We've talked about, you've been talking about functions for years. Do you remember the test for a function? What's the test for a function? There's a vertical line test, right? And there's also a numeric test. But that basically, if we had a graph, so let's look at an example. So let's look at the parent parabola. Is it a function? Yeah. I can draw a line, right? It passes the vertical line test. Well, to determine if a function is one-to-one, there's another graphing test. It's called the horizontal line test. And to be one-to-one is going to be significant for us with inverses. We need the function to be one-to-one to find its inverse. If it's not, we have to just artificially restrict it. They have to be one-to-one to get an inverse. Okay? So, let's look at this. Is the parent parabola a one-to-one function? It is not. It is not. So if we were going to find and you probably found this out last year in Algebra 2 when you were doing inverses of parabolas, you would get a radical, right? And you're like, wait a minute, these don't look the same. Well, that's because we need to restrict the parabola so that it is one-to-one. Okay, so that's just something that we need to be aware of. These two right here, this is a test that we can use if we're given two functions and they're asking if they're inverses of each other. We can use this test. So we would need to know, well, this is how we create them. We just switch the x's and the y's, right? That's what we do. We switch the x's and the y's. The test that we do is right down here. If I do a composite function of the inverses, I should get an x. So again, a composite function of the inverse, I can put the original function inside the inverse, I should get an x. If I put the inverse inside the original function, I should get an x when I have simplified. That's the test, an algebraic test that we can use to determine if functions are inverses of each other, is that. We do a composite of them. There's also a graphing way to determine if functions are inverses of each other. Remember that all inverses, they're going to reflect over a particular line. Do you remember what that line was? Y equals x. Y equals x. You can tell graphically if they're inverses of each other if you have a picture of them, a graph of them, and they reflect over the line y equals x. That's a graphing way. That's what we're talking about right here. That's a graphing way to tell if they're inverses of each other. Okay, so that's just a reminder of inverses. We have looks like a couple of examples to work. So let's work our couple of examples. So to find the inverse, they want us to find the inverse, and I'm also going to do domain and range so that we are really clear about what inverses are. Inverses are kind of a big deal. We looked at them, remember, last semester with trig. Remember we had sine and arcsine and how they were inverses of each other because their x's and y's switched. Remember that? I mean, it's a big thing, inverses. So here, if I want to physically find the inverse, I would switch the x's and y's and solve for y. That's what we're going to do. But before we do that, I would like to find the domain and range of this. We just finished a unit on graphing rationals, right? This should be pretty straightforward for us. Okay, I'm going to have an x, let's see, x equals -2 would be my vertical asymptote. My horizontal asymptote would be at y equals 1. And to get just a couple of points, let's see, when y is 0, x is 1. So we've got, and this one doesn't break through the horizontal. And just to look at the other section, let's just pick a -3 and I get a 4. So we know it's up there. So I can write my domain of my original function. My domain of my original function is going to be from -infinity to -2. And then it's going to pick up on the other side of -2 and go to infinity. That's my domain. And you can put the union symbol if you want to. If you just love that, you can do that. Parentheses is fine. Range, I'm going to go from -infinity and I'm stopped at 1. And then from 1 to infinity. Now, if we do this correctly, our new function should have those exact domain and range, but they should be flipped. Right? They should be flipped. And while we're looking at this, we see that graph. Is that a 1-to-1 function? Yes, it is. It would pass the horizontal line test, right? It would not. The horizontal line test says we can't cross through the graph more than one time. And there's no way we can draw a horizontal line and it crosses the graph at one time. So yes, this is a 1-to-1 function. We don't need to worry about any restrictions on it because it is a 1-to-1 function. So let's do the procedure for finding the inverse. We're going to take this original equation and we're going to change, make the x's y's and the y's x's. So this is going to be x equals y minus 1 over y plus 2. That is the inverse, but I'm going to be required to solve for y. That's kind of a thing that we have to do. I'll show you how I would solve this for y. So I would cross multiply, and I would say x times y plus 2 equals y minus 1. Okay, I'm going to distribute the x. So xy plus 2x equals y minus 1. I'm going to get the y's together on one side and move everything that's not a y to the other side. So I've got, it doesn't matter which way we go. So I'm going to do 2x plus 1 over here and y minus xy over here. Then what we want to do is we want to factor. We want to have one y. That's what I'm going for. So y times 1 minus x, just factoring. And my last step would be to solve for y, to divide. So y is going to be 2x plus 1 over 1 minus x. And if we did this correctly, our domain and range are flipped. So let's just flip them and see if we did it. Domain should be negative infinity to 1 and 1 to infinity. Is that true? It is, right? 1 is the only number that we're not supposed to have because it causes it to be undefined. Our range should be the other one's domain, so negative infinity to negative 2 and negative 2 to infinity. Is that right? Is that where my horizontal asymptote is? It is, right, at 2. So, great. And that's our very first one. Are we okay with that? So I wanted to do one that is a one-to-one function. We don't need to worry about restrictions. So sometimes I'll have you graph inverses. It's not going to be about, we're not going to be terribly worried about breaking through the horizontal asymptote. Okay, we're not going to get really complex functions here. They're going to be fairly straightforward. Okay. So on the next one, so the first one we did was one-to-one. This one, let's see, this is a radical. So let's graph this radical. Okay, so what would cause that to be 0? It would be a 4. Right? So it starts here and goes like that. Is that one one-to-one? Yeah, that's one-to-one. Okay, great. All right, maybe we'll do just fine. Let's do its domain and range. So I can look at the picture, look at the graph. So its domain, it starts at 4, right? And goes to infinity. What about its range? Starts at 0 and goes to infinity. Okay, great. Looking good. So now let's switch the x and the y and let's solve. So we have x equals the square root of y minus 4. So how do I release the y from inside there? I square both sides. X squared equals y minus 4. Solve for y. Y equals x squared plus 4. This graph looks like this. Well, that's a problem. Is that one-to-one? Nope. So I can't just use it. I can't just say, oh, that's my inverse. I'm going to have to restrict it. Right? I'm going to have to restrict it. It needs to match the side that I have right here. So I guess I have to ask myself, well, actually, it's pretty easy. I just look at this, right? I just look at my domain and range. I'm going to flip them. That's going to restrict it for me. I don't have to think about it. If we were going the other way, we would need to think about it. What if we had the parabola to begin with, and then we got the radical? So, well, it depends on which radical. If I have a positive radical, which side of this is going to go with the positive radical? The right side. And if I had the negative radical, which side would go with it? The left side, right? So it's pretty straightforward, right? Uh-huh. When you're turning a parabola into a radical for an inverse, before you can do an inverse for a parabola, you're going to have to restrict it. It has to be one-to-one. Okay, your function has to be one-to-one to get its inverse. Otherwise, you won't have an inverse. It'll be a relation. It'll just be weird. Okay, so for functions, we're dealing with functions. It needs to be one-to-one. So, okay, so we are going to restrict this, and we're going to say its domain is 0 to infinity. Okay, so we don't, let's redraw this. So we really only want this side. And its range is going to be from 4 to infinity. I'm just, again, reversing those. Okay, how are we? We okay? Okay.